Okay, let's get started. Okay, quiz 3 hopefully was not complicated. I think it's a fairly straightforward topic. And it's a fun topic, essentially. So what we're going to do today, okay, let's just quickly look at the syllabus. So today is lab day, which means we're going to play around an hour a little bit. We're going to go through the calculations again, just that you have a feeling for how to calculate things and how to solve practice lab 5, which is essentially posted already. And I also posted the code that we will discuss today. So that should be fairly easy. We will, in addition to that, briefly talk about practice lab 4. So there were some issues. Those of you that have posted and have seen an error that came out, that was the R version that you used that didn't load dplyr, the package dplyr that I used to summarize the respective subgroups. So I have remedied that problem, and the code that is posted circumvents the problem. And I will show you that in a second what I did. Next week on Wednesday, so Monday is no class. On Wednesday, we're going to do chi-squared test. Yes. Why not? Why? What? You're just canceling class? On Monday, not on Wednesday. Oh, the last time. No, I think next week. Like next week. Next week. Monday and Wednesday, and then that's it. We have no Monday, we have Wednesday. You're canceling Monday. I'm canceling Monday. Oh. No. No, we only meet on the 22nd, not on the 20th. What was meant to do? Yes. We have to come in for the final exam? Yes, unfortunately, it's well, fortunately, I have the pleasure to be here with you. And I'm actually. No, it is in person, and I explicitly got emails enforcing that it is in person. I thought about doing it, or I actually thought about having. Excuse me. Can we focus? Can we focus? Okay, so it's in person as an exam. I'm explicitly being asked to do it in person. It is a Friday, and I am well aware it's getting dark earlier. So they have for that Friday, they have essentially have an exception for that particular Friday. We have it, and we're going to start at noon instead of 1. So does this conflict with anybody's schedule? So it is timed by the leadership of Stern. So it should not interfere with your Stern tasks and assignments. So it should not. If it does, then let me know. Yes. Is it the same week as midterm? Yes. You think it'll take the same amount of time? It'll take the same amount of time, you think? Be prepared for a little bit more than an hour. More than an hour? Mm-hmm. How many questions is that? All right, just a second. We have. We can actually. We have final exam right here. That's going to be your final exam. We have 60 minutes for 30 questions. Oh, okay. I will. Yeah. It's on the computer, right? It is a computer quiz, yes. Good. So shouldn't be too difficult. Yeah, well, yeah. And it's the same like format as the other test? Pretty much the same format, but all the chapters. But what? All the chapters. All the chapters. Yes. All of them. Got it. Good. So we have next week, Wednesday, we have chi-squared. And we have on the 29th, we have a final review session. Are you all going to be in the city, right? I know. Oh, yeah. Yes. Is it really? Good. We can do it soon. Since it's study week, I'm okay with doing it soon if you're not here. You want to do it soon?
Yeah. It's
sure.
It's a review. It's a review.
It's a review class.
Yeah.
Yeah, let's do soon. It's fun. Then I also, yeah, sure, that's fine. And then I also volunteer again to give for you an excellent R review class, if there's appetite for that. I would schedule it on the 29th, 27th, the Monday on the 27th, on our regular time, because that shouldn't interfere with your schedules. It's 1 hour. Who's interested, log in, and we're going through some Excel question whatsoever, but it's voluntary. So it's voluntary for you, and I kind of recommend that you join, because essentially you will have Excel exposure.
So that's Monday at like 6:05?
Exactly, yes. I will do it at the same time.
And the 29th will be like?
The 29th is a regular class, but it's a review class. So we're probably not going to take the entire time. It's on Zoom. And the other one on the 27th is extracurricular.
So both the 27th and 29th on Zoom?
Yes.
And then we only have to request the next week on Wednesday.
Next week, Wednesday, is the last regular class, in a way, where we do something new. On the 29th, we're going to go over reporting, how to report statistics, and what tests to use, which is going to be important for your finals, because you basically get picked questions out of 150 multiplied by 18 chapters, right? So that's a large pool of questions, large pool of different topics. You need to recognize from which chapter this comes. So that's going to be the task at hand. So you need to kind of identify what test brain you got to switch on, right? So it shouldn't be a problem. You shouldn't be concerned about the finals. Like if you followed along and you're doing and you're doing what you just did on the quizzes, which you perform well, shouldn't be an issue. Okay. Good. Homework 3 has posted. Hope some of you have already looked at it, and I know that some have submitted already, and that's wonderful. If any questions, post to the discussion board, and let's initiate a conversation. Good. Practice lab 5. Any questions about anything concerning the syllabus, final exam, quiz? Okay. Good. All right. So for practice lab 4, we essentially were asked to reproduce what we did on that Excel spreadsheet, where we compared societies. This is 4. I just want to go through it quickly because there were some problems with the packages. So again, in R, you install packages. These packages have some certain functions in it. Sometimes these packages have hiccups. So in this case, the problem was dplyr. So this code here is essentially a grouping code where you take all the entries from society, which is in a long format where you have redundancies, but they are distinguishedly separated from each other by a separating factor, which is society. So you have society basically indicating from which society the entry was, and you have a scoring for each participant from each society. So this is why this is longer. This is 13 entries long. So you see it here, right? So this basically repeats foraging 4 times. So the first 4 entries are foraging, 3 entries are farming, then 3 entries are natural resources, and 3 are the industrial entries. So this brings that in a long format. And this is I mentioned this already before, you have wide format. And if you do analysis, if you get data from an analyst, you will never get wide format. It's like this is a rarity. Somebody does something in the wide format, it's always long format. That's why you have to be able to kind of distinguish one versus the other and know that there are different formats to look at this. So the way this essentially looks like, and I think I spoke about it already briefly, the way this looks like is essentially nothing else but what we did for the ANOVA. If you remember, we restructured, right? We calculated each individual score, and we calculated here the difference from the grand mean, which was down here, and it's in this long format. So the way that the long format is, when you look at it, it's a little harder to kind of get an overview, but R allows you to do that quite easily with this group by function. So group by essentially asks you for the data frame, which is DF1. Those are 13 observations, and separated by society, which is our distinguishing factor, which is here, with the 4 societies. Then we have summarize. It tells R essentially, okay, I want a summarization of that. I want a count, which is the number of entries for each societal level. Then we have a mean, which takes score, removes all the NAs, that's NA.rm equals true, says like remove all the missing values and only take those where we actually have an entry. And then standard deviation with the same, in the same format. So now the issue with that was if dplyr is not installed, it doesn't work. The idea was that it looks like this. Where we basically get for each society, we get a count, a mean, and the standard deviation, which is consistent with what we have computed in Excel. And so now just to put this in perspective, if you do this in Excel, it took us like a decent amount of time to get for each subgroup the respective mean. If you remember, we would like copy down and log in the grand mean and whatsoever, and it was like kind of tedious. Right? So now you do this in milliseconds and with 1 line of code. If you have a data set with like gigabytes of entries, dplyr is a package that was specifically programmed by the developers of RStudio. This is a very, how should I say, a very processor resource saving applications. So this will essentially, this function does the summarization in a fraction of all other codes in R. So dplyr I highly recommend it. So those of you that are analytically inclined, please flag the package dplyr. And the following version of it, the next generation of it is dtplyr, which also has database applicability. So you can actually use it, for example, to set up your own Apache Spark server and Apache Spark cluster. But that's too much outside of the scope of this class. So now what I did here as a workaround was essentially nothing else but creating society entry. There's a little object named society, has 4 levels. And then I'm running a for loop through it that iteratively repeats from 1 to 4, length of society is 4. From 1 to 4 repeats the whole thing and counts each time it runs through the for loop. It counts 1 and then adds 1, counts 2, goes through each code and does 1, 2, 3, and 4. And basically ends up in this. So when you run this, essentially you get the same thing, little clumsier, not as elegant, but coming to the same results. So you get for all 4 levels, you get essentially your summary, your mean, your standard deviation. Actually, no standard deviation. I forgot the standard deviation. So you can just reprogram it. In case you ever need something like that, you can reprogram it easily. Good. Did the same for the beer, and the ANOVA codes have not changed. And the ANOVA codes actually have remained the same, where we do an between groups ANOVA, and we do it within groups ANOVA, just in the same fashion as I've showed it in the other class. But this is enough about Practice Lab 4, because now the focus should be on Practice Lab 5. And I designed these practice labs in a way that it repeats what we did in Practice Lab, what we did in the actual class. And what we did in class was, just as a recap, we talked about absences from class, and we talked about bless you. And we talked about stressful life events and depression. As soon as my little Mac decides he's going to do that, we're going to be in Excel. So we did for the correlation example, we did a correlation between absences from class and the grade the student would achieve, hypothesizing that there will be an effect that is likely detrimental to the grade. So as soon as the Microsoft cards are with me and the display Excel, we can get started. What is this? Oh, yeah. Okay, so just as a recap, what we did. Okay, so this is the correlation. So we have a correlation. We essentially have here the exam grades. We need, if we calculate this by hand, we're calculating the deviations between x and mx. And with exam grade, and we calculate the deviations from y and my. The correlation coefficient per se is the sum of products between x minus mx, y minus my, and we essentially get to this relationship. When we look at regression, which of course did not open. Okay. When we look at the regression, we had the example of the stressful life events that are determining the BDI score. So essentially, again, we're calculating the correlation coefficient. We're relating then set x to set y by calculating set x from our individual x entries. We're relating set y hat to set x, and y hat is calculated from set y hat. By that, we get an intercept and a slope. We calculate SSY and SS error. We come to the proportional reduction of error, where we basically were relating the explained variability, the explained variance or sum of squares, to that total variance of our y. This will be our R square. So keep this in mind. So essentially, it is an R square that is determined by something that is quite close, when you think about it, to an F statistic, right? And this is essentially what you're calculating with a multivariable regression. You're calculating F statistic that exactly shows you the proportional reduction of your total error in your y, because essentially it doesn't make a difference whether your y is always a continuous variable, but it does make a difference for this computation if your x-axis is basically a nominal variable, or it's a continuous variable. And this becomes important when essentially looking at multivariable regression. So, but let's quickly walk again through the same example that we had for the correlation. So we're loading a data frame module 22. We get module 22 with our 10 entries, which looks exactly the same as the one we had in Excel. We can, with ls, function ls, gives you an overview of this data frame, shows you that it contains absences, grade, and the student ID. You can essentially pack every individual variable into separate objects using with the smaller and hyphen sign. You can also do it with an equal sign, but our coders prefer hyphen and the smaller sign. So this is essentially packing this in a separate object. So if I call now absence, absence is going to be identical with the variable absence in the data frame. So that's how I assign objects and variables into objects. Can do the same with grade. I'm not sure why I did it 2 times here. It doesn't matter. When you essentially want to now assign any particular entry, so with the core function, you get the correlation coefficient. This is the correlation coefficient that we also computed in Excel. So we have a minus 85, which we also had in Excel. We can pack this into our coef1 variable as I'm doing it here. So our COF1 variable is here essentially minus 0.85. You can, in the same fashion, you can also go along and use LM as a function. LM is basically building a linear model, which is essentially a regression of this association, which essentially shows you here, when you look at the summary output, which is somewhat consistent with what you see in the end of the regression example. You see here on top, you see the formula, LM formula equals grade as a function, and this is indicated by the tilde here, as a function of the absences observed in students. You get residuals. We talked about residuals. Residuals is the distance from each individual data point to the fitted line. So when you make a fitted line, this is how that fitted line looks like. So we essentially have here the plot that shows grades as a function of absences. So this is essentially the relationship. You can do this with the plot function that actually asks you for an x, which is our variable x absences, for a y, which is our variable grades. With xlab and ylab, you can label the x-axis and the y-axis. And this is the final product. You can export this as a PDF, you can export this as a PNG, whatever format of file you want to export it. It's very elegant to essentially show your associations. With the text function here, you can now implement on your graph. Oops. It's hiding. Okay. It's really early. Okay. With the text function, you can actually show your correlation coefficient on your graph. And you can add whatever text you want to add on your plot, which is quite elegant because essentially it's the same that you have done in Excel, where you have had to drag and drop, click and change, and manually change all these effects. Here in R, you do this with 3 lines. And the beauty of that is that these 3 lines, if you get additional data points, and this will happen to you, if you write your master thesis, you do projects down the road, sometimes during your further education, you get additional data in, you have an error in your data, you need to change something in your data. You don't have to go and change everything from scratch. You just rerun these 3 lines of code. And that's the beauty of that, because you're writing this code and this code is with you. You can adapt this to every application you want to apply it to. You can change things easily by just reprogramming it on the code, automatically exporting it somewhere as a PDF file, where you just have to take the PDF, take it an email and send it off. So this is the beauty of it. So programming makes life easier. It's a bit of a learning curve in the beginning, as those of you that have had some exposure know. But once you essentially master it, it's a lot of fun. It makes life really easy. So this is essentially what you're looking at. So you have here this model and the residuals, and this is what I showed you the last time in the end. Where's it go? So the residuals are essentially, so this is the regression function that we have calculated, which relates the intercept, which is here somewhere 95, and the slope, which is negative here because it's an inverse relation, and it's a decrease. It's defined as the decrease per 1 unit on the x-axis, which is number of absences. So it decreases with each absence a student had. It will decrease overall the function by a certain amount of grade. So you can estimate if somebody missed 4 classes, you can estimate, okay, so the grade is going to drop by 10%. So what does that mean? When you look here now at the residuals, you can, based on the residuals, you can say that this was not necessarily the best model of all times. And so you see this also with the R squared here, but we'll get to that later. But the residual basically gives you an idea how far away are your actual observations from your line. So the unit here for these residuals are essentially grade percent. And you see here that the minimal difference is minus 10.56. So this is one of these entries that is really far away from your actual function. Then you have the first quartile. So the residuals are basically nothing else but 10 data points, right? Each individual point, how far was it away from your fitted line? And these residuals, they have arithmetically, because it's like the deviations that we calculated, right? They center based on the way they were fitted, which is a regression method called least square, where you try to minimize the sum of squares. You essentially, you center your residuals around a mean of 0. So these residuals are normally distributed around a mean of 0 with the variability that is depicted here. So we have here an IQR that we could calculate, for example. So this is the IQR for the residuals. So this becomes very important. You remember this constant variance that we discussed, the homoscedasticity that was important for the ANOVA? This you can actually, you can essentially look at homoscedasticity, plotting this relationship. No, not this. No, like this. With plot LM, if you plot a linear model, you actually get into the diagnostic realm. You actually do diagnosis of linear regression models. And so now this goes far too far, obviously, and I know that. You don't need to know this for everything, but you can actually look at the residuals only. I'm just trying to amuse you here with what's going to come your way at one point. No? Or maybe not, if it isn't true. Okay, so you essentially, you plot these residuals, and you get the magnitude of your fitted values, and you look at these residuals, and you plot these residuals, and by that you can actually diagnose whether your residuals are actually constant and they do not change. So this is how you visually diagnose your linear regression model. Good, but enough about this. This is too specific. So there are various different ways how you would analyze that. Good. But back to what is actually subject of this conversation. Okay, so we have now discussed the residuals. These are up here. Then we have here the actual model. So this is our estimate. This is the S, and that's the intercept, right? That is the slope. That's the slope and the intercept, which we have calculated by relating ZX to ZY hat. This is the standard error, the variability around this fitted line. This is the corresponding t value, because it follows a t distribution, because the residuals are normally distributed. And this is the p-value resulting from the t distribution. The significance codes indicate whether your predictors were significant or not. And we briefly touched on those with our BDI score. Then we have residual standard error on 8 degrees of freedom. We have 10 entries with 2 groups. 10 minus 2 gets us to the degrees of freedom of the overall linear model. The R squared is the proportionate reduction of error by fitting this model. The adjusted R square is the proportional reduction of error adjusted for the number of covariates in your model, right? We talked about this. And here is the promised F statistic, which essentially is here 21.03. We remember from the ANOVA that every F statistic is basically testing against a normal distribution that is unimodal and right skewed. And we're determining a critical value on a degree of freedom of 1, because we have 2 covariates. The degree of freedom, the between groups degree of freedom is 1. with 8 degrees of freedom within degrees of freedom. So on the F table, if you would look this up and you would say, okay, so I have 1 between of groups freedom, 1 degrees of freedom between groups and 8 degrees of freedom within groups, you would find a critical value, which is here exceeded with an F statistic and F score of 21.03. As a conclusion of that, you get a p-value that essentially shows that your model is statistically significant in an F statistic. And then you basically determine the significant covariates. This is far too much information, and you don't need to recall all of this. I'm just giving you a glimpse of what's going to come your way at one point. So I also teach introductory statistics for graduate and applied biostatistics for graduate, and this is what you're going to do in your graduate studies when you do intro to stats. Okay. So now we do DFM23. Let's move on from the absences. We had enough of this. Now we move to individual entries, stressful life events. We have a back depression inventory score, and we have a sleep disturbance score. So we remember the last thing we saw in the multivariable regression was that the stressful life events did not determine the back depression inventory score. It was actually a sleep disturbance. So it's actually more important you sleep well rather than not having a stressful life event. So looking at this now in the same fashion, we get a correlation coefficient, which is here, what is it, 0.58, which is consistent with what we calculated in Excel. Then we get a fit2A. Our fit2A is here that regression that we basically constructed in Excel. We remember 9.5 was the intercept, 3.241 was our, what is it? Yeah. So 9.5 is the intercept, 3.24 is our slope. Now we're confirming the whole thing in R. Same intercept, same slope. We're looking again at the residuals. So when you look here at the residual, does anybody have an idea how we could find out whether it's indeed truly normally distributed? So we said residuals is the distance from each individual point to the fitted line. They are normally distributed around a mean of 0. How can we discriminate between a really normally distributed residual distribution or a not normally distributed residual distribution? Chapter 3, central tendency. We have a mean and a median. Why would we use a median over a mean? What would prompt us to rather use a median than a mean? Yes?
Maybe the curve, like where the curve is.
No. Ah, because, why?
Because if you have, like, the median is just the middle number, so it doesn't take in necessarily like what the numbers are. It's just like the order of them. So it's like the middle number, but the mean is like it would be included. So
Yes, you're shooting absolutely in the right decision, that direction. The actual reason in specific terms, the median is resistant against outliers. As you said, you're ranking them and we sorted them and we found the middle number, right? And it doesn't move with outliers. Only the mean moves because the mean is calculated as the sum of all entries divided by the number of all entries. So arithmetically, an outlier has to shift the mean. The median, bless you, the median doesn't move. So whenever you see a distribution like that, so min and max, they're like same ballpark, absolute values would be in the same ballpark. Median and the mean needs to be 0 arithmetically because you have a least square method and you fit that through and you say I want to minimize my least and my squares, my squared deviations, and that distributes around the mean of 0. And a mean of 0.35 versus a mean of 0 is not that much off. So that's how you discriminate between a skewed distribution or not. If you wanted to see on this distribution whether it's right skewed or left skewed, how would you do that? What would you look for? Yeah? The positive values or the negative values, yes. So the min and the max would give you an idea in which direction that actually could go, in which directions you may have more outliers, or in which directions you may have kind of a skewness. And also the first and third quartile. So these are the Markov distribution that would kind of like drive you in a direction and would kind of give you an idea. Also, the median would indicate in which direction it's skewed, right? But these are the things you're looking at when you compare it to a normal distribution. So what else? Okay. The same conversation here. So we have 10 entries, 8 degrees of freedom, 2 covariates, multiple R squared, 0.33. We found that. Adjusted R squared, 0.25. So it's getting a strong optimization for the added covariate. So now we have F statistics, 3.974 on 1 degree of freedom between groups, 8 degrees of freedom within groups. P-value borderline is significant was like 8%, like not really significant, but yeah, qualifies to talk about it as borderline-ish, I would think. So fit 2B, this includes now our sleep disturbance score. So respondents that did not sleep well, have a good evening. Those respondents that did not sleep well did essentially also score higher on the depression score. So they're more likely to be depressed. In essence, they're much more depressed, and they basically take the significance that we found here for our events, they take the significance away. So now only the sleep is significant, highly significant actually, right? So what you can conclude on that is actually that sleep is a much more important predictor of your depression score. And actually, once taken out, it may intersect to some extent. So then you remember how we had talked about partial correlation, where we have like this unknown third variable. It could also be a relationship like that. So if I were presented with the data, I would kind of like test the relationship between the sleep disturbance score and the events, which essentially we could do, right? Because we have R right here. So if we do, let's do IAT for interaction, is LM of DF M23 events. DF M23 events. No, but we will sleep disturbance go to the ST score. Because what could happen is that these dramatic life events could affect DF23. Here we're missing underline. That these traumatic life events do also affect sleep, right? So there could be an interaction. There could be an overlap, which we're not accounting for. Events was it. So if we do now summary IAT, we see how well designed that simulated data set is. And there's no correlation. So when you remember those Venn diagrams and they intersect, they're actually not intersecting that much. And it's not a significant model. So there's not much of an interaction. If there were an interaction, and this is again beyond the scope of this class, but you could include something that is called an interaction term. So you could take this, and now we do a new model, we say IAT modified, and we're including this as an interaction term by replacing that plus by a multiplication sign. And by that, we actually were getting in the realm of interaction diagnosis. So this is how you would test whether they're actually interacting. This plus this, and this plus this. So how here you can actually see, that there's a significant interaction when included in the same model. And that would actually show that there is an interaction that needs to be accounted for, because now suddenly the model becomes significant too. So these are the kind of things. This is my daily bread, right? And so you're investigating in the data what else could play a role. Your hypothesis could play a role, and then you're investigating it in data, and you're meaning to display that in a way that it informs the community of what could have interactions. Okay. So this was a lot of information, not all of it relevant, but good to have seen one day. Okay. No, but you will see this again. I promise you. So you have, so this is our zoom, our zoomed plot. Was it? So this is that relationship between the stressful life events and our back depression inventory score. And this is consistent with what we've seen, right? A correlation coefficient around 0.6, which sounds a little high. Oh yeah. Also, don't forget, so this is 0.6. It's depicted 0.58 is rounded to 0.6, which I did deliberately here. We can actually leave 2. And so the R square here in the model, in the first model, is what is it? 0.33. So for a univariate analysis only, you can essentially take 0.58 square, and it is close to your R squared. So this 0.58 of this correlation is the correlation coefficient. If you square it, it becomes 0.33. This is not true for any other model. So there's no correlation coefficient as soon as you have more than one variable. So correlation coefficient is just indicating correlation between 2 variables. There's nothing to do with the R squared in anything that is beyond 2 variables. So don't think in that direction at all. Good. Yeah. Any questions? It's fun to see, right? It's like it's because by that you really can test additional variables. You can test different hypotheses. You can, and this is usually nice. So now let's go a little further in my world. So we have here a software that is called Dagity. You remember how I talked about directed acyclic graphs? So directed acyclic graphs is something that you actually will plot. So this is from the realm of epidemiology. So you're looking for an outcome, where our outcome was the back depression inventory score. If we take this score and we want to depict an association between life events and back depression inventory score. No. No. That's not good. No. We have changed the functionality here. Okay, PDI. We're doing events, live events. So now we have sleep disturbance. And we know now that sleep disturbance affects PDI. But we also know that sleep disturbance and life events are also related. So you're more likely to have sleep disturbance when you have life events. So that being said, you can depict now this as a so-called acyclic graph, directed acyclic graph for basically life events affect PDI, sleep disturbance affect PDI, and life events affect sleep disturbance. So this is how you would depict such a relationship. And you can actually, here with causal effect identification, you can actually change the depiction of how you want to depict things. It's a little different, I've changed. So here it actually would give you summaries of your association. It gives you causal paths, and it kind of analyzes this for you. It kind of even gives you codes for models, which you can save here. So when you want to you reuse such an association, you map out your entire network, your causal pathway network. You can save this code, and you can essentially reproduce it and add to it and discuss it. You can even import this into R, and R will depict it for you. And it's nice to depict it in some papers. It's a nice way of depicting these pathways. Testable implication, you can actually have Daggerty do in a way some associations for you. You can use different ways of depicting this. All right. Any questions on that? It's a nice tool to kind of show, right? Sleep disturbance is your exposure. Your outcome is sleep disturbance is this exposure. Right. Latent exposure outcome adjusted. This PDI is here outcome. So we get here in red, we actually get the, I actually want this to be exposure. This is adjuster. Okay. So this is how you would depict this. Okay, any questions on anything? All right, and have a nice evening.
Thank you.
Thank you. Feel better, Marcela.